Okay, let's unpack this. Imagine trying to predict, well, every single flicker of electricity, demand and supply, across an entire system, hour by hour. And not just predict, but actually optimize it. Find the least cost way to keep the lights on for everyone. Yeah.
Right, well, making sure the businesses involved can actually make a profit. It sounds like a monumental task.
It really does. But that's exactly what these market economic simulations are trying to do for the energy sector.
Indeed. And today we're diving deep into, the intricate world of these simulations, specifically focusing on a model that's designed to pinpoint that least cost solution for a whole electricity system.
Okay.
Our source material lays out a really comprehensive procedure for this. It even makes a distinction between the business economy, that's where taxes and subsidies are factored in, and the socio-economy, which looks at the broader societal costs, sort of stripping away those specific financial levers.
And our mission today really is to take this quite detailed document and pull out the most important nuggets for you. Think of it like a shortcut, maybe.
Yeah, a way to grasp how these complex systems are set up to balance profit and demand in the power sector.
We'll uncover how the model thinks, what it prioritizes, and how it connects to some very real-world energy challenges we're all facing. It's actually quite fascinating when you see the logic start to unfold.
It is.
So, at its heart, this simulation, it's all about balancing electricity demand and supply to find, well, the best price, right?
Yeah.
How does it actually figure out the price of electricity for any given hour across this huge system?
Well, it starts by calculating something called net import.
Net import, okay.
Which is basically the total electricity demand in a region minus its total electricity supply at that moment. And the demand side is incredibly granular.
How so?
It covers everything from basic home and factory electricity needs, right through to flexible loads, things like charging electric vehicles or the power needed for heat pumps, even hydrogen production.
Wow, okay.
And the supply side is just as detailed. It includes, well, all sorts of generation. Traditional power plants, nuclear, renewables like wind and solar, hydro, geothermal, and various types of CHP units combined heat and power.
Right, the ones making heat and electricity together.
Exactly. And the key insight really is that this level of detail lets the model spot subtle inefficiencies, find opportunities for optimization that simpler models might just miss, especially now as our energy systems get more decentralized and, frankly, more dynamic.
That's a powerful level of detail, I agree. So once you have that net import figure, how does that become a market price? Is it a direct link?
It is, yes. There's an external market price. The model calls it PX. It's determined by a sort of baseline price first.
Okay.
But then it's adjusted based on a dependence factor and, crucially, the amount of net import or export.
So if you're importing more.
Exactly. If the system is importing a lot of electricity, the market price goes up. If it's exporting, the price goes down. It's a very direct reflection of basic supply and demand across borders. It really shows how interconnected these energy markets are.
That makes perfect sense. Okay, so moving from that big picture market price, the model then zooms in on individual generating units using this concept it calls balanced production. Can you explain that? And maybe what's the big implication here for a future grid, one that's relying more and more on varied sources like wind and solar?
Right, balanced production. It's essentially the output level from a specific power plant or unit where its marginal production cost, the cost of producing 1 extra megawatt hour, precisely matches the market price that results from that production.
Okay, so it finds the economic sweet spot for each unit.
Pretty much. It's how the model optimizes each individual unit within the system. For example, take a geothermal plant. To find its optimal output, the model first figures out the market price without any geothermal power. Then it calculates exactly how much geothermal production would bring its specific marginal cost into balance with that market price.
Ah, I see.
And the really profound insight here is that it forces every single generating unit, whether it's a huge nuclear plant or a flexible geothermal one, to operate at its precise economic optimum in real time.
Dynamically adjusting.
Yes, dynamically. And that dynamic adjustment is absolutely crucial for a grid with lots of renewables. It ensures that flexibility is properly valued and used, letting the system stay stable and cost-effective, even when wind or solar output fluctuates.
And I understand it also has to consider the physical limits, like transmission line capacity. Does that capacity act as a hard limit on this net import or not? You mentioned that choice can really change things.
It absolutely does. Deciding whether transmission capacity limits imports and exports is a critical setting. It directly affects how much the external market can influence domestic prices and production.
So it reflects different grid philosophies.
Exactly. Are you prioritizing maximum market integration, letting prices flow freely, or are you perhaps more focused on local grid stability and maybe a degree of self-sufficiency? That choice matters.
Okay.
So we've kind of set up the building blocks now: demand, supply, price, how they interact. Now, let's maybe zoom in on the model's actual workflow. You could think of it like a dance with many steps, constantly adjusting to find that best, least cost solution.
A choreography, I like that. Okay, let's unpack this choreography. What's the very first step?
Step one is really about setting the stage, defining the electricity market itself. That includes how external prices change hour by hour and how imports and exports affect them using that dependence factor we talked about.
Right.
Then step two identifies all the marginal costs, both for production and consumption.
So the cost of making one more unit, or using one more unit.
Precisely. Factoring in fuel, taxes, CO2 costs, variable operational costs, all usually expressed in a standard unit like DKK per megawatt hour in the source material. And this step also defines the profitability rule. Essentially, when does it make financial sense to sell power versus buying it?
So it lays down the rules, the costs. What's this sort of starting gun? What kicks off the calculations?
Step three sets the initial prices within the system. It looks at the total demand and the production expected from renewable energy sources, RES.
Okay.
And this step involves a really critical choice, almost a philosophical one.
Okay.
It's about variable renewables like wind and solar. Can they be curtailed? Meaning, can their output be deliberately reduced if market prices go negative?
Right.
Which implies there's too much power.
Right, an oversupply situation.
Or alternatively, will they not be curtailed? Will they keep producing even if prices are negative, perhaps because of subsidies or other factors?
That reflects very different ways of managing renewables, doesn't it?
It really does. It's a key policy debate. And just as a starting point, the model usually assumes all district heating is initially covered by standard boilers.
Got it. That's a fascinating detail in renewables. So after setting those initial conditions, what's next?
Steps 4 and 5 then switch focus to optimizing electricity consumption.
The demand side.
Yes. First, the model looks for the cheapest ways to meet specific, flexible demands. Things like producing hydrogen for transport fuel, or optimizing when electric vehicles charge, or providing hydrogen for small micro CHP systems.
And this is where things like smart charging come in.
Exactly. Smart charge for EVs, which optimizes when they charge based on price or grid conditions, and also vehicle-to-grid, V2G, where EVs could potentially feed power back to the grid.
Now, delving into that demand optimization, the V2G strategies seem particularly interesting, especially when you think about the practical side. I gather the model looks at V2G in 3 different ways.
Precisely. And it's a great illustration of balancing the ideal with the real world.
How so?
Well, it can simulate V2G with no limitations, which the source itself points out may, however, lead to severe power plant and grid capacity problems. It's kind of the theoretical maximum,
The dream scenario, perhaps.
Maybe. Then there's a version with a limitation based on the actual capacity of power plants and transmission lines. That's obviously more realistic.
Right.
And finally, there's a strategy aimed at minimizing PPmax power plant maximum. Here, it actively tries to schedule EV charging and discharging specifically to reduce the peak load on the big power plants.
Yeah, trying to flatten the peaks.
Exactly. And this really highlights the practical hurdles and policy choices involved in integrating potentially millions of EVs onto the grid without causing major problems. It's like the difference between just imagining a future highway and actually designing the on-ramps and traffic flow.
Makes sense.
Yeah.
So after optimizing these essential flexible demands, does it then look at other ways people use electricity that might respond to price?
Yes, step 5 moves on to optimize a whole range of other electricity-consuming options. Things like replacing traditional boilers with efficient heat pumps, or maybe electrolyzers in district heating networks, or switching from basic electric heating to heat pumps in individual houses. It even considers using electricity to produce steam for high-temperature thermal storage.
Interesting.
These options are sorted by their marginal consumption costs, starting with the highest cost options first. And importantly, every time the model activates one of these consumption changes, because it's adding demand, it inherently pushes the market price up.
Right. More demand equals higher price, generally. So
Yeah.
the logic is, first, optimize how you use electricity efficiently, and only then figure out the best way to produce it.
Exactly. It's a logical sequence. So step 6 then optimizes hydropower and concentrated solar power, CSP, production. It takes into account their unique features like water storage for hydro or thermal storage for CSP and their generator limits. Then, step 7 tackles all the other electricity production options. These are sorted the other way around by their lowest marginal costs first.
So the cheapest power runs first.
That's the principle. This includes nuclear, geothermal, large condensing power plants like traditional coal or gas plants, and various types of CHP units. And each time a production unit is brought online or increased, it does the opposite to price. It tends to decrease the market price.
Supply goes up, price
Yep.
goes down.
Exactly. And the model is constantly checking against transmission limits here too, making sure total exports don't exceed line capacity. And if import capacity from outside is hit, it might activate more expensive domestic plants, like condensing units, to meet demand.
This really paints a picture of the system prioritizing based on cost and impact, constantly tweaking that market price as it goes. What's the sort of grand finale of this optimization cycle before it repeats?
Step 8 is about optimizing electricity storage. That could be hydro reservoirs, batteries, or even compressed air energy storage CAEs.
Okay, storage.
And this part introduces a particularly interesting strategy called the EnergyPLAN out-for concept in the source.
What does that do?
It's quite sophisticated. Instead of just reacting to the current price, this strategy makes bids on the market based on the average price expected over an upcoming period, which the user defines.
Looking ahead then.
Yes. It calculates a minimum selling price and a maximum buying price around this predicted average, using various factors to ensure it makes a profit. It's a clever, forward-looking way to manage storage assets for maximum business profit, not just simple arbitrage.
That does sound advanced.
Mm.
And then you mentioned in step 9, it repeats steps 3 through 8. Why does it need to loop back if it seems like it did a thorough job the first time?
Because every single decision made in those steps, consuming a bit more here, producing a bit more there, charging or discharging storage, every single one subtly changes the market price.
Okay. The ripple effect.
Precisely. So repeating those steps lets the model refine its calculations. It ensures that the cumulative impact of all these decisions on the market price is fully captured. It's an iterative process, like honing an answer through successive adjustments, leading to a more accurate, stable, and truly optimized final result.
That makes sense. It needs to let the dust settle and recalculate. And finally, step 10 deals with critical excess production. What exactly is that, and how does the model handle it?
Critical excess production, or CEP, is basically when the simulation finds there's way more electricity being generated than can possibly be used, stored, or exported. Often happens with very high wind or solar output during low demand periods.
Right. Too much of a good thing sometimes.
Potentially. So step 10 calculates how to manage this surplus. Usually it involves curtailment, deliberately reducing generation from certain sources. And the model incorporates the economic consequences of that unused energy. It ensures the final solution is technically feasible and the economics account for everything, even when there's a potential flood of power on the grid.
Okay, so beyond just balancing supply and demand in theory, the simulation tackles some very real physical grid challenges like bottlenecks. Is that right?
It absolutely does. Section 7.2 is, in the source material, specifically describes how the model handles bottlenecks.
Which are?
Situations where the amount of electricity trying to flow either out export or in import exceeds the physical capacity of the transmission lines connecting different regions.
Like a traffic jam on the power line.
Exactly like that. And when a bottleneck occurs, the model effectively separates the external market from the domestic one. They operate independently for that period. The domestic market price is then set by the marginal cost of the power plant that's kind of at the edge, the one causing the bottleneck. Or, in cases of that critical excess production we just discussed, the price could even drop to zero domestically because there's simply too much power penned in.
So a bottleneck literally creates two different market prices, one inside the constrained area, one outside. That feels like a real aha moment. And I think you mentioned there's a financial side to this too, not just operational.
That's right. It's quite interesting. If there's a bottleneck, a profit is actually generated because electricity is effectively being bought at a lower price on one side of the constraint and sold at a higher price on the other side.
Who gets that profit?
Normally, it's shared equally between the transmission system operators, the TSOs. Those are the entities managing the grid on each side of the bottleneck. And notably, this model includes half of that price difference as an income in its socioeconomic calculation.
Ah, tying back to that earlier distinction.
Yes. It shows how profits generated by these physical market limitations are viewed when assessing the overall societal benefit versus just a company's bottom line. Of course, if there's no bottleneck, the domestic and external prices just stay the same.
That's a surprising detail, how infrastructure limits can create these financial flows.
Okay, one last crucial point. What about grid stability? Is that just assumed, or does the model actively check it?
No, it's not just assumed. It's a critical safety check at the end. Section 7.11 describes how the model performs a vital check on grid stability requirements.
So after all the economic optimization.
Exactly. After finding the theoretical cheapest solution, it checks if that solution would actually keep the grid stable and running reliably. Things like inertia, frequency control.
The technical stuff that keeps the lights on.
Right. And if the simulation finds that stability isn't met, maybe there's too much fluctuation from renewables without enough backup or inertia, the model adjusts the output of traditional power plants.
Oh.
Typically, it increases their production to ensure the system remains stable. So it overlays a reliability constraint on top of the economic one. Precisely. It's a crucial practical step, ensuring the least cost solution is also operationally sound and, frankly, safe. Wow. We have covered a remarkable amount of ground today, from the basic idea of finding that least cost solution through the complexities of market pricing, demand management, optimizing supply, strategic storage, and even these real-world issues like bottlenecks and grid stability.
It's quite a journey, isn't it? This deep dive really shows how you can model such a complex system, accounting for countless variables, optimizing for profit, yes, but also aiming for efficiency and reliability. It's really a testament to structured thinking when trying to understand these incredibly dynamic energy markets.
It really is. And it shows how grid operators have to balance so many competing priorities constantly. So as you reflect on how a model like this identifies the least cost solution, maybe consider this. How might just a small shift in our behavior, maybe widespread adoption of new energy habits or some unforeseen technological breakthrough, how might that fundamentally change the optimal pathways this simulation finds? What new challenges or maybe even surprising opportunities might pop up from those changes that even these really comprehensive models would need to adapt to?